Okay, next we're going to talk about single-slit diffraction. And this is the diffraction of a light wave or particle through a tall, narrow slit. So notice that the slit width is small, and then the slit height is much bigger. And notice that the pattern, my diffraction pattern, my interference pattern over here is in the same direction as the smallest edge of the slit. So the diffraction pattern goes with this smallest side. So if the small side is horizontal, then my diffraction pattern is horizontal. And that's because the light has to be really close together. So we just wouldn't see the diffraction pattern from, or the interference pattern from, a large slit. It would be so small that we wouldn't see it. This needs to be really small in order for us to see a diffraction pattern. And we can see it's similar to our double slit pattern, right? We have these bright bands, and the thing to notice that's different is that we have a big central band compared to the other. Let's see if I can go back. If you look at this band here, each of these bright fringes are equally spaced. And if we go back and look at the one for a single slit, right? So that one, when we saw them equally spaced, is for a double slit. This is two slits here. But for a single slit, we can see that they're not equally spaced, that the bright fringe is much bigger than the side fringes. And so these are called secondary maxima, and they're weaker. And so just to go over this again, the pattern on the screen is due to a narrow slit that is, and so you have to pick horizontal or vertical. So think about that for a minute or two, pause the video and see if you can come up with an answer. And I'll just restart again. Okay, so the answer is vertical. So we have this slit that has a large opening in the vertical direction and a small opening in the horizontal direction, and that's where we get this horizontal pattern. So here we have just the side view of our single slit interference experiment. So we have A is our slit opening, and remember when we were talking about double slit, we had two slits. So the slit opening length is A, but the distance between the slits was D. So here we're just talking about one slit, one opening, this A. Our L is the distance from the slit to the screen. We can see that we have a central maximum here. And so notice this central maximum is pretty big. And that, if we just go back and look at that last slide for the double slit, we can see right here, we have these fringes, right? But we have this envelope outside. And so this envelope on the outside here, the envelope of my orange fringes represents the single slit diffraction pattern. So this single slit, you can see it's big, so it's bright in the center and then falls off. And that's what causes the fall off of the brightness on these interference pattern due to the two slits. But this would be my central peak when I'm looking at, in this example, this central peak, right? If I were going to add another slit, I would have a whole bunch of fringes inside of here. And so we can use the equation in a minute, but the smaller the peak, the smaller the slit is, the wider this pattern would be. So I can control this size here of the central slit by this. One of the ways is the slit width. Notice here also that when I'm talking about m lambda in the double slit, I'm talking about p lambda here, and p is representing each of the orders, but now we're talking about the dark fringes, so where there isn't light. So here, right, we're looking at the black, where the black is. So I would be measuring, this would be P1, this would be P2. So my P1 and my P2 here. So that's what I'm going to be measuring, and when I reference my theta, I'm going to be measuring theta for the line drawn from the center of the slit to that first dark spot. This equation, theta P is equal to P lambda over A, actually comes from Young's double slit. So if I have, let's make this an A sine theta is equal to P lambda. Oops. Sorry, I think I will try to erase that. and start over and make that look a little better. So it's going to be A sine theta is equal to P lambda. And so for small angles, and that's like for, say, theta less than or equal to 1 degree, we can say that sine theta is the same, about the same as theta. So if I plug that in, A theta is equal to P lambda. And so then that's where we get this equation, theta is equal to P lambda over A. So that's where that equation comes from, and that's making this assumption that this theta is really, really small. And now this other equation, W, so W is the width from here to here. And so so if I think about that, that's the same as my Y. So I'm going to say this is Y sub P. And so if in double slit, we use tan theta was equal to, so remember this is my theta, and so I have a triangle here. So opposite, tan theta is opposite over adjacent, so that's going to be YP over L. And so then if I use the small angle approximation, that means that theta is going to be YP over L, right? Because for the small angle approximation, sine theta is about the same as tan theta. And so if they're both small, then theta is the same as tan theta or sine theta. So that's where this comes from. And so if I plug that in, then I can say theta is equal to YP over L, and it's also equal to P lambda over A. And so that means that YP, let's see if I can, I know I'm all over the place here, but I'll go up here. So YP is equal to P lambda L over A. You see I'm getting there, P lambda L over A. And so if I want the first one, I'm going to have Y1 is equal to lambda L over A. And W is just equal to 2 times, so W is equal to 2Y. And so then I get the 2 lambda L over A. So that's where this equation comes from. So we also have a diffraction grating, another diffraction application, and this consists of n closely spaced slits. So we now understand the single slit, we have the Young's double slit, and now we have lots of slits. So you can see they're very close together. We have n of them. We get to use the same equation again, right? The bright fringes occur at d sine theta is equal to m lambda. D is the separation between two slits. The y position of each fringe, remember, so tan theta is equal to y, this height, over L. And so ym is equal to L tan theta. And where the order of the diffraction pattern is m is equal to from 0 to however far you want to measure. I'm just going to erase what I have down here that came through. Okay. So here's just another view. So if I zoom in, I can see that I've got, or I guess zoom out, I can see that I have lots of slits over here. So all of these are separated by D. And so we have these peaks here, right, for that represent our peaks. So if we go back and think about this equation, right, those that would be m lambda. So those peaks would be at those locations. Right, so I'm going to see something that looks like this. So comparing the interference pattern of a double slit, so this would be my double slit, right? And this is going to be my diffraction pattern, so my grating. And the nice thing here, if you notice, is if I send in 2 different wavelengths, right, I'm going to get separation between, say, the two different colors of purple here because they're slightly different wavelengths. So I'd be able to detect that very well with a diffraction grating. And I'm just going to skip. So a diffraction grating is illuminated with yellow light. The pattern seen on the screen behind the grating consists of 3 yellow spots, one at 0 degrees straight through and one at 45 degrees. You now add red light of equal intensity coming in the same direction as the yellow light. The new pattern consists of an orange spot at 0 degrees, yellow spots at 45, and red spots slightly further out. So as wavelength increases, theta increases. So looking at our equation, if lambda increases, then theta increases. And so red is farther out than yellow because red has a bigger wavelength. And they blend at the center because m is equal to 0. So if m is equal to 0, then theta is equal to 0. So we don't have any blending. So the only place we're going to see a difference is out at any m greater than 0, and we'll see larger separation at larger m's. And so an interference pattern is formed on a screen by shining a planar wave on a double slit arrangement. If we cover one slit with a glass plate, the phases of the two emerging waves will be different because the wavelength is shorter in glass than the air. If the phase difference is 180, how is the interference pattern shown left altered? So here, the bright and dark spots are interchanged, right? So if the phase difference is 180, remember, so if I think about a sine wave, let's see if I can turn this up a little bit. All right, so if I think about a sine wave, so this is one wavelength, and this is also 2 pi in phase, and this is also, if we think about the phase of a sine wave, and this is also equal to 360. So if the phase difference is 180, that means we're here. So the phase difference is a half a wavelength between these two. And so if we have a half a wavelength, that means that they're going to be out of phase. So it's going to go from bright to dark or dark to bright. So they're going to be interchanged because they go from constructive interference to destructive interference when the phase is changed by the glass plate in front of one of the slits. So we can use this idea of diffraction gratings really for some really neat applications. And so this is spectroscopy. So what we have here in the two pictures is the one on the left. This one here is this is a handheld. This one right here is a handheld spectrograph. And what we can do is just look through on the shorter side and look at different lamps. So we can look at a hydrogen lamp or a sodium lamp or helium lamp, and we would see these different patterns on so this is our diffraction grating is on the bigger side and would point that at the light source, would look through with our eye on this short side, and we would be able to see something like the scale that you see just below it. And the different lamps would create this diffraction or this spectrum, right? And we would see different colors, and we could use that signature to be able to determine what element is the filament of the lamp is made of. And so we can see the different ones here. This is an example. The one on the right is an example of a spectrograph attached to an iPhone, and you can see the spectrum with the application on the iPhone. So here's just another example of what reference spectrum, what we would see for different kinds of lamps. So we can also talk about, so far we've just talked about square or rectangular apertures, but we also have circular apertures, and they're very much, there's lots of applications with circular apertures. You can think of astronomy. In astronomy, usually there's a mirror or there's lenses, and the light comes through hits that mirror or comes through those lenses, and you have a circular aperture. And so a circular aperture creates a diffraction pattern that looks like this, where there's a central peak that's made of a circle, and then you have concentric circles around there. We have just one slit, so we can see that the central this width is bigger than the other rings, and this is called an airy disk. And so 1/2 the width of an airy disk is given by this formula. So the math to derive this is beyond the scope of this course. But theta 1 is equal to 1.22 lambda over d. And this actually comes from something called Bessel functions in math. And this would be the first term of the expression of the Bessel function. So you might see that when you're a senior in a math methods class or in graduate school. But circular apertures are really important for astronomers, right? Because the circular apertures, the mirrors are circular, and d here in this example refers to the diameter of the aperture. And the airy disk, the size of the airy disk determines the resolution of the telescope. So that just means, can I distinguish between two different stars? And the airy disk created by my telescope is going to tell me how close those stars can be, or how far apart those stars can be. Sorry, how close those stars can be in order for me to be able to detect them with my telescope and not see them as one image. There's also applications, right, for cameras, for microscopes. So the airy disk and circular apertures come into play in lots of different areas. Here's an example of an interferometer. So this is called the Michelson interferometer. And the way it works is we have a light source here, and we have a beam splitter. And so what a beam splitter does is, it's a very good name for it. It splits the beam. So half of the beam is going to go to mirror 1, and half of the beam is going to go through to mirror 2. So this beam splitter has a 50% reflection transmission property. So it's like half silvered. So some of it goes through, some of it goes up. And then when it comes back through, it uses that same 50-50. So some of it comes from mirror 1, the light comes through to your eye or to a detector. And from mirror 2, the light bounces off and comes through. So for the first mirror, the path is going to be source, reflects off the mirror, goes to the mirror 1, comes back through the beam splitter to the eye. The second path is going to go through the beam splitter, bounce off mirror 1, come back, reflect off the beam splitter, and go to the eye. And so if these two, what you're doing is determining the phase difference between the paths of these two beams. And so the constructive or destructive interference occurs based on the path difference between L1 and L2. And so we can say that L2 minus L1 is equal to m lambda over 2. And why isn't it just m lambda? Well, remember that the path is going to be, it's going back on itself. So that's where we would have m lambda. So if we're off by half, it's multiplied by 2 because it comes back on itself from the mirror. And so it uses very precise changes in distance, and it can measure the wavelength of light. I used this when I was a graduate student working at NASA. I was working in an optical fabrication group, and what we did is we were grinding mirrors, and we also were grinding some lenses, and we used a Michelson interferometer to measure the flatness of the mirror as we were creating it. So imagine if my mirror wasn't perfectly flat, I would be able to pick up on those changes or those differences from my flat mirror, say M2 was my reference flat, and I would continue to work on this mirror 1 until it got to the right and got to a certain number of fringes that it met the quality standards that we were looking for. This is an example of the Michelson-Morley experiment, and you'd learn more about this if you take modern physics. But the idea was that back during this time, they knew that sound waves needed air to travel, and they knew that that water waves needed water, right? Waves in water needed water. So light must need some sort of a medium to travel in. And so they came up with this idea that it was the ether. So they wanted to be able to measure the ether. And so they were thinking, well, we can measure if we're moving and the Earth is moving, is moving. And so if there's an ether, then we should be able to detect a wind. And that wind is going to make in whatever direction it's in, it's going to change the speed. And so we should be able to pick that up with our interferometer. And so they did this experiment, and they found, so the idea was I should be able to bounce off of, so use a beam splitter and send some of the light in one direction and send some of the light in the other direction. and if the Earth is moving, then in one of these arms, right, I should see a difference. And so I should be able to detect that using this interferometer by comparing the two paths of light, one not going through the wind or perpendicular to the wind, and one going through the wind. And what they found was that there was no difference detected. And so they came to conclude that there was no ether, and this led Einstein to develop the theory of special relativity. And this is our final application of interferometry. The LIGO facility detects gravitational waves. And so I think it was 2015 was one of the first observations. The important things here is that this facility actually has two interferometers. And so that way they could make sure that, that since the signal that they would be detecting is so small, they needed to make sure that it wasn't due to something else, that the noise or something like that. So they actually have two facilities, one in Louisiana and one in Washington State. And they are able to read signals and be able to compare them. And if they see them on both, then they'll know that they've detected a gravitational wave. They're detecting tiny, tiny, tiny differences in between the two beams of light, and so that's what they're doing. They're measuring two paths of light, beam A and beam B, and if there's a difference, they're able to detect it very precisely. The interferometers need to be 4 kilometers long. So each of those interferometers are 4 kilometers long, and they're measuring teeny tiny changes. They're very, very sensitive.